All right, in section 2, we're going to go back and review a couple types of functions, mainly our linear equations, our polynomial functions, and our piecewise functions, all which are used pretty prevalently in calculus. So a linear equation, something you did in Algebra 1, is something we use quite a bit in calculus when we start talking about derivatives and things like that. A linear equation, recall, is any equation of the form ax plus by equals c. So something x plus something y equals c. Now, it doesn't have to look like that. A lot of times, remember, we would solve for y and do y equals mx plus b. That's also a form of a linear equation. But the big thing is you see no exponents. You just see something with x, something with y equal to a constant. And there are other things as well. Obviously, if you graph a linear equation, you're going to get some kind of line. It could be a slanted line like this. It could be a horizontal line. It could be a vertical line. Those are all going to be our linear equations. So if we look at these three equations here, I'm going to claim that only one of them is a linear equation. Now, the first one is not a linear equation because remember, it has to be something x plus something y, and this one has a product of x and y. So that is not linear. This is actually a reciprocal function. This would look something like this if I were to graph it. Now, the second one is a prototypical linear equation. It's actually written in the correct form and everything. It's something x plus something y equal a number. So this is definitely a linear equation. So if I were to graph it, I'd see some kind of line, something like this. And again, always graph these on Desmos or your graphing calculator, check what the graph looks like. Now finally, this one we have y equals 2 to the x plus 8, which looks similar to our slope-intercept up here, but it is not, because you have the x in the exponent. So this is an exponential function, exponential equation, so this is not a linear equation. So the big things we're going to look at with linear equations, we're going to look at their graphs a lot, but the big thing is we're going to look at their slope, and we're going to look at the equations of their lines. One of the big things in calculus, we know how to do slopes of lines. It's going to be very simple. You've did it lots of times. But there's also going to be ways to do slopes of curves. So when I look at a curve like this upside down parabola, I'm going to claim that this has a slope as well, and the slope actually changes throughout the domain of the function. Now, a regular old slope, if you recall, slope is kind of the slant of the line, how much the line slants. And there's lots of ways to say it, but the equation for slope between 2 points, we would say is y2 minus y1 over x2 minus x1. A lot of people will also call it rise over run, how much you go up versus how much you go over. All these are ways to do the slope. Also, like we spoke of before, if you have an equation in y equals mx plus b, then m is the slope. So if you have m as your slope in an equation with y by itself, then that is your slope. Just a couple things about slope that you probably remember. A line that's going up has a positive slope. A line that's going down has a negative slope. A horizontal line, that's not a very good horizontal line, but if it's flat, you have a slope of 0. And finally, if you have a line going straight up and down, this has a slope that is undefined. So those are the 4 types of slopes we'll see in our linear equations. And really, when we start doing some other things with slopes of curves, these are the kinds we'll see as well. So let's do a couple examples where we're finding the slope. So the first one says, find the slope between the 2 points. So essentially here we have 2 points. We'll call this point x1 and y1, and this point x2 and y2. Now that's just arbitrary. You could switch those if you'd like. But remember, the slope is going to be y2 minus y1 over x2 minus x1. So if I plug those numbers in, I'll get 7 minus 3, and then I'll get negative 2 minus 2. You could switch both of those, the 3 and the 7, and the negative 2 and the 2, but just make sure that you switch them both. So that would be 4 over negative 4, so that's negative 1. So this would have a slope of -1. So it'd be some line slanting down on our graph. Now the second one you see, it says you have the line 3x plus 4y equals 12. So we can't use the y equals mx plus b here because the problem with this equation is it does not have y by itself. So the first thing I'm going to do is I'm going to get y by itself. So I'll subtract 3x to both sides. So I get 4y equals 3x plus 12. And then I'm going to divide everything by 4. So y is going to equal -3/4 x plus 3. And now, because this -3/4 is the number in front of x, that is going to be my slope. So this would be an equation that is slanted down. So going from down when you go left to right. So once we find the slope, it's also sometimes helpful to find the equations of a linear function. So when you have some information about the line, so maybe I have 2 points or the slope and a point that the line passes through, we'd like to find linear equations. Well, if we recall, a linear equation is just y equals mx plus b. So really the only two things I need to find the equation of a linear function is the slope and b, which is the y-intercept. Now there's lots of ways to do this. The textbook we're using uses what's called point slope, but I'm just going to use y equals mx plus b, and I'm going to show you how I can find the equation of two types of lines pretty simply. So this first one says I want to find the equation of a line with a slope of y equals -4 and passes through the point 5, -13. So I'm going to write my answer up here. So I know it's going to be y equals m. Well, if this is the slope, this is m. So it's going to be y equals -4x because it's mx, and now it's plus b. Well, 5, -13 is not b because it is y-intercepts are always 0 and some number. So this is not the y-intercept. So we're going to have to do a little bit of algebra to find its y-intercept. So to find the y-intercept, I'm going to do y equals mx plus b. Let's write my generic equation. And what I have is I have m, but I also have an x and a y. So if I plug those in, I get -13 equals -4 times 5 plus b. So what I'm going to get is I'm going to get an equation that I can then solve for b. That's going to be -13 equals -20 plus b. And then I'm going to add 20 to both sides. So that's going to give me 7 for my b. So I'll write that on my equation plus 7 because that's going to be my b. And this is going to be my linear equation. So if I were to graph this, if I were to put this on Desmos or your graphing calculator and I were to plot it, I would guarantee it has a slope of -4, down 4 over 1, rise over run, and I guarantee it would have a y-intercept of 7. Now the second problem is pretty similar. The only problem is in this case it doesn't give us the slope. So we're going to have to start by first finding the slope, which we can do with y2 minus y1 over x2 minus x1. So that's going to be 7 minus 3 over -2 minus 2. This is one we did up above, so it's -1. So I know my final answer is going to be y equals -1x, and then some intercept, so I'm going to do the same thing I did up above. Y equals mx plus b. Now, I actually have 2 points of x and y, so I can pick either one. Just for fun, I'll pick this one. So I have 7 equals -1 times -2 plus b. That's 7 equals 2 plus b, and then I'll subtract 2 both sides. So b equals 5. So my final equation is going to be y equals -x plus 5. So that's kind of the family of linear equations, and we will use these quite a bit as we start getting into the actual material. All right, our second class of functions we're going to look at are polynomial functions. Now, polynomial functions are going to be any function of the form f of x equals a to the n x to the n plus a to the n minus 1 x to the n minus 1 all the way down till you get to a constant. So this is a very fancy way of saying, all right, you're going to have some highest power. Let's say the highest power is 7. So you have x to the 7th. We'll have some number in front of there. And then we'll have maybe a smaller power. Maybe we have x to the 6th with like a 4 in front of there. And then maybe we have a x to the 3rd. Then at the end, we're going to have a constant, or you could have a constant of 0, so something like that. So this is a polynomial function. So you study polynomial functions a lot in Algebra 2 and pre-calc. But the big thing about polynomial functions is all their graphs typically will work the same depending on what this highest power is. Okay? So we call that highest power the degree. So for an n greater than 1, all degrees that are odd, so 3, 5, 7, 9, all those things have a graph of an S-curve. So it's going to kind of look something like this, or it could be upside down like this. And there can be little bumps and little changes in the graph along the way, but that's the general idea. And then all even degrees will have a graph of a parabola. So if I have, say, a 8th degree function, it might look something like this. Now, it could do lots of little things like that, but in general, you're going to see it looks something like a parabola. And again, it could also be turned the other way. It could look like that. So any equation, really, its graph is, any polynomial function, its graph is really determined by that highest power by the degree. Now, one thing we will use a lot is the concept of end behavior. So end behavior is where the graph goes as x tends to positive and negative infinity. So let's go ahead and look at an example of this, kind of explain this a little more. So let's say I have an odd degree polynomial equation that looks something like this. Even though there's some bumps in the middle, it basically looks like some odd degree polynomial function. So for its end behavior, as x goes off to infinity, so as the x values get bigger, as the x values get larger and larger and larger, what happens to the f of x values? What happens to the y values? Well, the y values, as the x's go up, the y values get higher and higher and higher. So the y values or the f of x values go to infinity. As x goes to negative infinity, so as the x's go this way, you'll see that the y values, the f of x values get smaller and smaller and smaller. So they go to negative infinity. So end behavior, very important. We'll tie that a lot into when we talk about limits in our chapter 2 as we go to infinity. Finally, the last thing I want to talk about with polynomial functions is a zero of a polynomial function. And again, just like the zero of any function, the zeros are going to be values. Let's just call them r, because sometimes zeros are called roots, such that f of r equals 0. So we're going to try to find values that make it 0. And we'll look at a couple ways to do this. We can look with a graph, because remember, zeros are also x-intercepts. We'll also use things like, for quadratics, we know we have the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So we can use that one as well. So I want to go ahead and look at a couple examples. So when you go through these examples, what I would encourage you to do before we do each one, go ahead and graph it. We'll do the algebra, we'll think a little bit about it, and we'll make sure our graph verifies what we're thinking algebraically. So this first example, f of x equals negative 2x cubed plus 2x squared plus 12x. So the first thing I want to point out is we have an odd degree. So we know the graph is going to be some kind of S-curve. Now, we'll never get a perfect idea of the graph is unless we graph it, but we'll get some really good ideas about it. You can go ahead and graph it, pause the video, graph it, see how it looks. Before we start, if you'd like, that's fine. So when I'm trying to talk about what the graph looks like, though, I know that it's an S-curve, and I know it's going to be turned upside down, probably something like this. Now, the reason I know it's turned upside down is we have the negative in front. If you have a negative in front of your leading term, it's going to basically be flipped. Instead of going up, it's going to go down. And a parabola, instead of pointing up, it's going to go down. So now that we have kind of a sketch, we know our end behavior. As x goes off to infinity, so as x goes this way, the f of x value is going down in this case, because you can see the y values go down. And as x goes to negative infinity, so as you go this way, the f of x values are going up. So that's our end behavior. Now, as far as zeros, you can kind of see that I just kind of roughly put some zeros in here. I don't know if those are right or wrong, but we can check. Because what we're going to check is we're going to see where is 0 equal to negative 2x cubed plus 2x squared plus 12x. Now, of course, on your graphing calculator, you can kind of just look at the graph and kind of estimate where they are. On Desmos, you can actually point to them and it'll tell you. But if you want to do something like this, what I would start by doing is I would first try to factor out what I can. And I see I can factor out a negative 2x. They all are divisible by 2 and x. I just like to pull the negative out to get rid of it. Now finally, if we look at this one, we have an even function because our degree is 4 and the number in front is positive, so this is going to look like some kind of parabola. So something like this, maybe some stuff down here, who knows, and going up. So you can see that end behavior, as x goes to positive and negative infinity, the f of x values are both going to infinity, both going up. Now, as far as zeros, this one's a little more involved. You'd have to use rational roots theorem and things like that. But I'm just going to look at my Desmos graph, and I see it crosses at 3 and -3, and nowhere else. So my zeros are going to be at x equal 3 and -3. And for something equation like this, that's sufficient for now. There are lots of techniques that hopefully you've seen in the past to solve those, but for now, we'll just use the graphing calculator for some of our more high degree equations, how to solve them. The final kind of function we're going to look at here is what's called a piecewise function. So a piecewise function is a function which takes different values in different intervals. So depending on what your x value is, it might be a parabola, it might be a line, it could be something else. So we can just very informally try to draw what a piecewise function. Let's say I have a line going up, and then let's say this graph decides to turn into a parabola, and then it's going up, and then let's say it stops here with an open circle, means it doesn't quite get to that point. And let's say it jumps down here, and then it becomes a flat line, a horizontal line. So this would be an example of a piecewise function. So you can see in the 3 intervals, from here to -infinity, it's a line. From there to there, it's some kind of parabola. And then from that point to the right to infinity, it is a flat line. So those are the different ideas you could see as you're doing this. So as I look at my first piecewise function, it has only 2 parts. It has parts that are less than 0 and parts that are greater than or equal to 0. There are lots of ways to do this, but a pretty simple way to do this is I'm going to make a little table. And for this first part, it says I want to graph the line, the function x. So I want to graph f of x equal to x only for x values that are less than 0. So I'm going to pick 0, -1, -2. Now you might be asking yourself, why did I pick 0? 0 is not less than 0. Well, it is the first starting point. It's kind of the breaking point. So I'm just going to write open next to that, and I'll show you what that means here in a second. So the functional value, the y value, is going to be the same as the x value. So this column is just going to be the same. So I have 3 little ordered pairs. So I have -1, 1, -2, 2, and then I have an open circle at 0, 0. And then I'll just kind of connect that because I know it's some kind of line. So it looks like this. So it's open there because it's going to get as close to that 0 as you want, but it's not going to quite touch it. And then I'll do the same part for my other part of my graph. I'm going to say that the function equals x squared when x is greater than or equal to 0. So I'll do the same thing. I'll do 0, 1, 2. And 0 in this case is a point. So 0, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So if I plug that, you'll see that these two do connect. They don't have to connect. And then 1, 1, and then 2, 4. And this kind of goes like this. So it's a line, it's a straight line, and then it kind of curves up and makes it kind of parabolic. So you should always kind of have one continuum. It's still a function. None of these are not functions, so it's just still past the vertical line test, so all that still applies. So a couple follow-up questions. It says, what's the value of f of 2? Well, when I plug in 2, the question is, do I plug it in the top part or the bottom part? Well, since 2 is greater than 0, I'm going to plug it in the bottom part, so 2 squared, so that's going to be 4. When I want to know f of 0, well, 0 is also going to be in this bottom part because this is for x greater than or equal to 0. So this is going to be 0 squared, which is 0. So those are my 2 functional values for this function. Let's look at one more example. So the easiest part of this one, which has 3 parts, is going to be this middle one because it says when x is 0, that the function is just 5. So that's just going to be 0, 5. So that's just going to be a dot right there. Now the other 2 parts, a little more involved. So we have f of x equals x minus 2 when x is less than 0. So I'm going to do the same thing, 0, negative 1, negative 2, because those are less than 0. But again, that 0 in this case is going to be open. So I'll plug these x's in. 0 minus 2 is negative 2. Negative 1 minus 2 is negative 3. Negative 2 minus 2 is negative 4. So there's my point, 0, negative 2, which is going to be open. Negative 1, negative 3, and negative 2, negative 4, which looks like this. So it definitely does not connect to that dot up there. So the other part, we're going to have f of x equal to 3 minus 2x, and when x is greater than 0. So 0, 1, 2, and again, this will be open. So 3 minus 2 times 0 is going to be 3. 3 times 2 times 1 is 3 minus 2, which is 1. And 3 minus 2 times 2 is negative 1. So we'll get 0, 3, which is going to be open here, 1, 1, which is here, and 2, negative 1, which is here. So there's our points there. So the follow-up question says, what is f of 0? Well, f of 0 is defined by this middle part, so that would just be 5. The other part of this one, it says, what are the intercepts? Well, just looking at this, I can tell you the y-intercept, where it crosses the y-axis, is 0, 5, because it's right here at this point. Now, x-axis is just going to be this little portion here, which is our third portion. So it's really, where is 3 minus 2x equal to 0? So if I solve that, negative 3 equals negative 2x, divide by negative 2, so x equals 3 over 2. So I'll go ahead and I will post this video, and I'll post another video on how you can do some of these on Desmos as well, the piecewise functions, because that'll be pretty helpful because we will have to graph quite a few of these this year. So if you have any questions on section 2, please send them my way, and let me know.